Yes, she does. Okay. And to do slides forward, just like space, right arrow, or click. All three will work. No. We are 1 minute from the start time. This is much closer to expected for the starting time. I might give it another like minute or two. Yeah. Also, we're now being recorded, so now we need to stop saying stupid shit. Yeah. Damn. It's unfortunate. It's most of what I say. Oh well. I'm sure we'll manage. And we'll find a way to stay stupid. We'll find a way to say stupid shit in a smart way. Yeah. Given how many people are still trying again, I'm happy at like 2 or 3 more minutes. Yeah. am now going to show everyone shut up. Wow, you guys are so good at that. Okay. So hello, my name is Nick. I'm in my 4th year of a pure math degree. I ran the 135 review session. I recognize some of you from there. This is Zev.
Hello, I'm Zev. I'm in my 3A term of pure mathematics. I did not run the previous session, but I'm very happy to be running this one.
So just before we get started, I would like to manage a couple expectations. This session is not teach you literally everything that ever happened in 137. 137 took like 12 weeks, and I'm good, but I'm not that good. Instead, the focus of this session is going to be on going through important theorems and a couple of very specific good questions with a focus on intuition, on how Zev and I think about these problems, think about these theorems, how we come up with solutions, how we conceptualize these things. There will be review of content of theorems, whatever, but the focus here is going to be on intuition and problem solving. Now, this room is not that big, and there are a lot of you. If you are talking to your neighbors or to people in the aisles or whatever, the people around you cannot hear. That's a real dick move. Please do us a favor and be quiet. If you have something so important you need to tell your friend, you're allowed to step out for a minute and come back. But for the love of everything, stay quiet. Okay, so in terms of, is this going to work? Yes, this is going to work. Yeah. So the first thing we're going to go over is study tips. How do you get from where you are, which statistically speaking is about a 60 on the midterm, to doing well on the final? And how do you actually understand and retain this content in a way that you will be able to do well in Math 138? After that, we're just going to be going through practice problems and proofs of a few major theorems. And kind of these are the main things we'll be going through. Epsilon n sequences, epsilon delta continuity, EVT, IVT, derivatives, Newton's method, and mean value theorem, and of course, some Taylor series. So I feel like this is a good point to get started on study tips. I gave this same little speech when I did the 135 review session, but I'm going to do it again. So most people who get into their 1A study as follows. They get a practice midterm or assignment, and they maybe try and solve it for a little bit. Then they get stuck. Then they look at the solutions. Then they read the relevant part of the notes when they don't understand the solutions. Then they go back and read the solutions again. They understand it this time. They go, wow, I'm doing such a good job. And this is not unreasonable coming from high school, because in high school, you were able to do well in your math classes knowing how to solve problems. If you knew how to take a derivative, you could get a 100 on every test in high school math. Unfortunately, this has changed. Knowing how to take a derivative does not help you apply the mean value theorem. And so there kind of needs to be a fundamentally different approach. And that approach will change in both where you're solving problems and when you're reading the notes. And what I have written here as my first point is just reading is completely useless. You need to be reflecting on things as you go. Throughout the presentation, Zev and I will be doing this. We'll be talking about how we think about theorems, our intuition for them, but we don't have time to do this for every theorem in the class. You guys need to do this too. When you read a theorem, the mean value, intermediate value, extreme value theorem, a random lemma, a computational corollary, whatever, you need to be asking yourself, why does this make sense? Why does this fit into the math I already know? How does this piece together with other things? The mean value theorem almost directly follows from the intermediate value theorem. That is a connection that does not get mentioned in Math 137, but that you can absolutely intuitively make on your own. You need to be understanding why the theorems are true and how you come up with the proofs from the intuition. Kind of the second thing that I have here, and then I'll let Zev talk for a bit, is that 137 has a lot of rules. You have your big lists of derivative rules. You have your tests. You know, you have the test for if this is a min or a max. You have the Taylor series formula, et cetera, et cetera, et cetera. A lot of people think that studying means sitting down and memorizing these rules one by one. Again, this is not effective. Almost all of the rules from 137 have a geometric intuition behind them. I, as a person, still do not know the second derivative test. I do not remember whether second derivative positive means max or min.
But if you give me 30 seconds and a piece of paper, I can rederive it. And I will be talking you guys through that derivation today. Being able to do that is substantially more valuable than being able to state the second derivative test. Because with my thing, having the intuition to figure it out on my own, I can modify it, I can change it, I can from my intuition, figure out how to prove it. And so I can tackle a much wider set of second derivative test problems than someone who just sat down and memorized it. Basically, every rule in 137 can be learned by intuition. It can be rederived by you. Your goal should be to understand these rules to a point where you don't have to memorize them, not to sit down and know all of them by heart. With like, and the ones that are kind of really stupid that you will have to memorize, I'm pretty sure they give you a reference sheet. No? Oh, that's dumb. Okay, memorize the derivative rules then, and nothing else. Everything else you can do like by understanding. Zev, do you have anything to add?
Yeah, I just like stressing even more how important it is to understand what's behind these theorems, because when you see a question that wants you to use, this theorem, like whatever theorem, the question isn't going to look exactly like the definition of the theorem, and you're going to be able to plug in the numbers and do everything right. I was doing an assignment the other day, and it took me like 2 hours to figure out that I had to use the intermediate value theorem. And this is a 4th year pure math course. So if I went through every list of theorems I know, it would have taken me a lot more than 2 hours. But I was able to sort of see what was going on. And that's what you need to be able to do with this kind of thing.
Yeah. The last thing I have here is stop looking at the fucking solutions before you try things. Oh my God. This is okay. If you read the solutions every single time, you have taught yourself to be really good at reading other people's solutions. The skill they are testing on the 137 exam is your ability to come up with solutions. Yes, there is value in solutions other people have written. Once you have solved it, you can compare. If they have a better solution, you can ask, how did they come up with it? Why did I come up with something different? But before you solve the problem, and before you've spent like minimum 5 hours, stop looking at the solutions. Oh my God. Looking at the solutions is not effective. Of course, because this is an exam, you also need to be ready for time pressure. So like practice is good, timed practice is also good. Make sure you do both.
I would, I had a few things. I would say timed practice should probably come once you are comfortable with like regular practice, because otherwise it might stress you out. And so for this reason, do not start studying the day or 2 days or 3 days even before your exam. You know what the main reason is? You need to sleep. Because if you, not just for your health, but if you start solving a problem and you can't figure it out and you're like, oh, I really want to look at the solution, there's no way I can figure it out. If you sleep, then all that info that was in your brain gets put together into a nice package that makes it a lot easier for you to understand it when you wake up. And you might even be able to solve it when you wake up. I cannot count the number of times this has happened to me.
Yeah, I have actually dreamed solutions to assignment questions before. Getting enough sleep is obviously very important for your health. It is also biologically proven to be necessary for retention. You will not remember things if you don't sleep after you study. So that's kind of what we have in terms of study tips. Does anyone have any questions about how we study, like how this would be implemented, whatever? You can also think of on this now. We will be doing a Q&A at the end. Okay. So then without further ado, let's get to our favorite 137 theorem. This is the single most important theorem from the entire course notes. The triangle inequality. Woo!
Yay.
Now, the triangle inequality might be the most intuitive statement I've ever seen. It says that if I walk from the point X to the point Y, it will be, that will be shorter than if I walk from the point X to the point Z, and then the point Z to the point Y. That is all that the triangle inequality says. It is a statement about distances. Absolute value is how we measure the distance between real numbers. And by the way, there are like a bajillion equivalent forms for this inequality. They're all the same. You get them by clever substitution of variable. However it was written in your course notes, this is the version I most like to think of, because this is the version that's clearest in terms of distances. Absolute value x minus y is the distance from x to y. Absolute value x minus z is the distance from x to z. and absolute value y minus z is the distance from y to z. So like reading this like this makes a lot of sense. You guys have seen the proof of this. It's basically a case bash. I'm not going to waste your time with it. But what I'm going to let Zev talk about for a bit is how you know when to use the triangle inequality.
So I kid you not when I say not an assignment has gone by since my first year when I did not use the triangle inequality somehow. Well, depending on the course. But one good way to know that you have to use the triangle inequality is if you ever see an absolute value sign anywhere, then you might have to use the triangle inequality. I think another version, I'm going to give a different intuition behind it than the one Nick gave. A version that you're probably also familiar with is the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And what's very helpful with this is if you imagine your x and y as like things that have lots of dimensions, you know, like even real numbers, it might be positive, it might be negative, right? So when you add x and y together, parts of them might cancel each other out and make the total length or the total size of x plus y smaller than the sum of its parts. But when you take the size of them before that, the absolute value of x plus the absolute value of y, that can't happen. And so in a lot of cases, if you're trying to prove that something is this less than or equal sign, we're going to see this a lot when we start working with limits, but proving that a thing is less than or equal to another thing is often just as valuable as proving that a thing is equal to another thing, if not more, because it can often allow you to reduce problems to simpler cases. So a lot of the time, you'll have the first thing in those absolute value signs. It's going to be nasty, and you're not going to know how to deal with it. But the second thing, your z might be like a really, really easy sort of thing to work with. And you might be, by splitting up that absolute value, just making everything a lot easier. Heck, you might be making your x minus z and y minus z into things that you already know the value of, or you already know that they are less than some other thing.
And we will be making this concrete. There's a problem we're going to be working on right after we get through like convergence of sequences that will use this principle very exactly. But I think it's worth talking about the triangle inequality in isolation just because of how important it is. Oh, that was the wrong button. So one of the like intuitions that I have here, the second one I've put, is that if x is close to y and x is close to y and y is close to z, then x is close to z. I have my letters flipped on that. But here we have, if this distance is small, the distance from x to z is small, and the distance from y to z is small, then the distance from x to y is also small. And this is how we often use this. We kind of reduce a limit question to showing that x and y are both close to something we pick z, where z is kind of cleverly chosen. And we will be seeing this very concretely in a few slides. So with that out of the way, we're going to talk about epsilon delta. I'm going to take this slide because I'm a bit of a math history nerd. So who here did an epsilon delta proof in high school? Raise your hands. That's about right. Who here was able to do calculus in high school? Like, you know, take derivatives, maybe integrals, whatever. Yeah. So a lot of people like kind of, they see that. They go, I could do calculus in high school, but I could not write an epsilon delta proof. So why is this class making me write epsilon delta proofs? Well, one of the answers, it makes you better at proofs, it makes you better at logic, but there are actually historical reasons. So, wrong mouse button. So calculus was originally done using what are called infinitesimals. If you haven't heard of an infinitesimal before, Newton basically went, pretend there's a smallest number. And other people went, but there's not. And he went, but pretend. And using infinitesimals, he was basically able to prove all of the things we do about derivatives. His definition of a derivative was f of x plus infinitesimal minus f of x over the infinitesimal. And this was like literally all the computations he did were the same as what we did, replacing the infinitesimals with a limit as h goes to 0. But the difference was, since infinitesimals don't actually work with the real number, you can't add them, subtract them, divide by them, multiply by them, proving theorems became really hard. Newton was able to do computational calculus. Newton was able to do physics, you know? He was able to compute the derivatives of functions. But we are mathematicians. And even if you're not interested in pure math, even if you're a CS student, or you're going into stats, or you're going into like finance, you still care about theorems, because almost everything that we do has some underlying theoretical backing. And proving something like the intermediate value theorem is only possible when you have a formalized framework of like concrete definitions to work with. You know, if I say pretend infinitesimals exist, there's nothing precise there. There's nothing to work with. The epsilon delta definition is very consistent and works purely internally. And kind of, it was either Cauchy or Weierstrass who introduced this. Sorry, Weierstrass, depending on who you ask. But either way, like once this was introduced, we had a surge in analysis and a bunch of new theorems were discovered and proven. And like much of modern math originates from their work. So the reason you're taught about epsilon delta is, yes, it's interesting, and yes, it teaches you how to do proofs. But the main reason is this is the setting you need to be able to develop more sophisticated theorems. And like with that in mind, let's talk about sequences.
Yeah, so a sequence. You have a bunch of terms. They are countably many terms, one for each natural number. It goes A1, A2, A3, you know, yada, yada, yada. And it converges to some limit. It might, your sequence might converge. It might diverge. It might go and get infinitely big, or it might go all around in a not nice way, but it also might converge to a limit L. And the intuition behind convergence is if they get and stay arbitrarily close to that limit. And arbitrarily close is just another way of saying that infinitesimal thing, but in a way that kind of exists. Now, here's the formal definition. And I know there's a lot of like weird letters and stuff. You know, we don't want, when we have a definition for something so simple, it's easy to get overwhelmed by just the sheer amount of things. But I think a good way to, I've included a picture here that sort of shows the intuition behind it. So this is a sequence. You know, you got your dots that are going to the right? So as our n gets bigger, we have our ANs, which change, right? And this, it's easy to see. If you just look at a sequence, you could be like, yeah, I can convince you that that's converging to this L here, right? They're all getting really, really close to it, and they're going to get even closer over time. Like they're getting really, really close. But what does this definition have to do with that? I'll read out the definition since I haven't done that yet. So the limit as n approaches infinity of AN is L if for all positive distances epsilon greater than 0, there's some cutoff point big N, so that for any little n greater than or equal to big N, that distance from AN to L is smaller than epsilon. So we can see, in order to prove that a limit approaches something, you have this epsilon, right? Or I guess we're not talking about proving it. We're just talking about why does this definition make sense. Well, look at this epsilon here. This is the epsilon, right? And after a certain point, after here, all the dots are within that little distance, right? And so that's why this definition means that. And if I make my epsilon even smaller, like if this dotted line is getting closer to that red line, I have to move my n further, because now this might not be there, this one might not be there, but maybe further, they'll all be there. So for every small distance, there has to be a cutoff point that allows you to get there. It might be really, really far. If I make that epsilon super, super tiny, I might have to move my n so far. It might take a long time to get there, but as long as it's eventually really, really close, that's all we care about.
I would also just like to talk about the value of this kind of picture. I'm so glad Zev included it. I think everyone here has pretty good intuition about functions, right? In high school, you took functions and advanced functions and calculus, all of which are about functions, whereas sequences were like maybe a unit once. Sequences are functions, though. Sequences are functions from the natural numbers to the real number, right? For each natural number, you're taking a real number. And what that means is you can plot them just like functions. And oftentimes, drawing the points of a sequence gives you a huge amount of intuition about what's going on in a theorem concerning sequences. I would also like to note that what Zev did for that definition, that why does it make sense draw a picture, you should be doing that on your own for every single definition. If there is a definition that does not make sense to you, if you read something and you go, this seems arbitrary, this doesn't make sense, do this, draw a picture, come up with an idea. And if there are any definitions you haven't been able to figure out, you can ask us about them during the Q&A. Now, we have a really good intuition here. Let's do a concrete example. So I don't know if the 137 course notes still do this, but here's roughly how every epsilon delta proof was presented when I was like at first year. Let epsilon greater than 0 and let n equal some bullshit. The bullshit was kind of never really explained. And then they would compute that that value of n actually worked, that made the sequence converge. This is backwards. This is not how you, a mathematician, write this proof. This is how you, a mathematician, present this proof to your audience. What you as a mathematician do is compute the distance between an and L, and you manipulate it until it's in a useful form. Then you pick the n based on that form. So let's see this. I'm going to let an be this sequence. So n plus 3 over n squared minus n plus 1. Prove the limit as n goes to infinity is 0. And at this point for you guys, this is a pretty straightforward thing. But I'm going to talk about how I would think through this problem. So the first thing you should do when you get any question in any course is convince yourself that it is true. Why should the limit be 0? Well, okay. Intuitively, this is not a proof, but this is a very good intuition. Intuitively, when n gets really, really big, n plus 3 and n are roughly the same thing, right? Like 1,000,000 and 1,000,003 are almost exactly the same multiplicatively. And similarly, n squared minus n plus 1 is basically n squared for, again, very, very big n. And so this means that for very, very big n, our function or our sequence roughly looks like n over n squared, which is just 1 over n. And that clearly goes to 0. Now, the question is, how do we formalize this? I bring up the intuition for a reason. The intuition is going to help us. So I'm going to just manipulate this expression, and this is just going to be some algebra, but I'm going to manipulate it very intentionally. I'm going to manipulate it so that the numerator looks like n and the denominator looks like n squared, so I can do this kind of canceling. And introducing inequalities is fine, because when working with limits, you don't need like the distance between an and L to be equal to some small quantity. You just need it to be smaller than that quantity. So the first thing, okay, we're showing it converges to the 0, so I'm measuring the distance between it and 0. And since this sequence is always positive, I drop my absolute value bars. And then I noticed, okay, I can, for like n greater than or equal to 3, I can replace the numerator by 2n and only make this strictly bigger, right? Because I've replaced 3 by n, and if n is bigger than 3, that makes it bigger. And so now I'm like first step of the way to getting to our intuitive picture. Now the numerator actually does look like n. And similarly, I noticed that I can make the denominator smaller and make the whole fraction bigger. So I can remove this plus 1 and like not still have an inequality. And now this is really, really promising, because now we can factor n out of everything, right? So this is just equal to 2 over n minus 1. And now crucially, we have bounded the distance an minus L strictly in terms of n and some constants, but constants are fine. And now that we have this bound in terms of n, we can just pick, like given any epsilon, we can pick the n that makes this original expression smaller than epsilon by making 2 over n minus 1 smaller than epsilon. And making 2 over n minus 1 smaller than epsilon is really, really easy. You can just pick n equals 4 over epsilon plus 1. And I'm going to leave it to you guys to verify that that works. But kind of the crucial thing here is, when I was writing this, I did not look at the question and go, I'm going to use 4 over epsilon plus 1. No, actually, I did do that when I saw the question. That's because I've done a lot of these. That's not how humans write proofs, though. You look at it, and then you kind of go, okay, let's screw with this until we get this in a useful form that I can actually extract information out of. And once I had this in this 2 over n minus 1 form, it was really easy to pick an n that worked, because it's easy to make this expression smaller than epsilon. This is how you approach writing these proofs. And in fact, one of my professors, Blake Medill, take a class with him if you ever can, he's blessed, would always at the start of these proofs write n equals question mark on the board and just keep that in a box. Then he'd go through the whole computation. And then once he got to this step, then he would go back and fill in what he had for n. And this is how you write these. This is so important. You do not need to be able to look at a question and figure out the n that works. You need to be able to manipulate it into a form where you know the n that works, which is a very different and much easier problem. Okay, I think that example is fine.
Yeah.
So, you want to take this?
Yeah, sure. So, sometimes instead of being given a sequence, we're asked to prove something about all sequences. And proving something about all sequences is a very useful thing because then you're getting to prove general results that you can then use on other stuff. So you might be asked to prove something like this on your final, or you might recall something like this that you proved and try and reprove it to help you with a problem. But it sort of makes sense that these kind of things will exist. So if we look at this, if AN converges, yeah, so these are just things about different sequences, and we're going to figure out how to prove some of these things. So yeah, this isn't a statement about every sequence, this is about convergence. So the second thing, right? Yeah.
By the way, just quick notational thing. I'm not sure if you guys have seen this. I'm writing AN arrow A as a shorthand for AN is a sequence which converges to A because I'm getting tired of writing that. I don't know if this is shorthand that 137 uses, but I will be using it throughout the slides. Just the arrow to mean converges to.
Yeah. And it's really important. I want to take a minute to talk about the importance of these sort of abstract proofs, because especially if you're going into pure math, your days of seeing numbers are all but over. Like I have seen like more letters than numbers this term in math calculations. I've can't remember the last time I saw the number 3. This is how math is done. You prove general things. So, and you even see this now. I'm sure you are going to be asked some kind of general result like this. And proving stuff about everything, that's what math is. Because if you prove something, if you prove that a singular sequence approaches 0, yeah, that gives you intuition about how to work with sequences. That gives you might give you some helpful info. But what does it tell you about all sequences? Nothing, because that's one sequence, right? So that's why this kind of thing is very important. So I'm going to focus on the second thing. So if AN converges, then it is bounded. That is a thing as well. But if AN approaches A and BN approaches B, or if the limit of AN is A and the limit of BN is B, where here AN and BN are terms in a sequence, then the product approaches the product of the limits. Now, this makes sense intuitively. Try and convince yourselves of this for a minute. If I have two sequences, like separate, of real numbers, they have nothing to do with each other, but they're both approaching a thing, the product of all the terms will approach the product of the things. Now, intuitively, this makes sense, but how are we going to prove this kind of thing?
We do go through the bounded proof first.
Yeah, we're gonna do that. Oh, okay.
It's like it's a nice, easy warm up. The product question is quite hard. The bounded question is kind of a little bit easier.
Do we have a slide for it, or are we just?
I think we have a slide for it.
I think we're moving right on to this.
Yeah, no, I prove it here.
Oh, okay, you did. All right. Sorry, we are going to talk about the if AN converges, then it is bounded. I must have zoned out when I was reading that one.
So yeah, then I can take this one because I have a nice. So kind of the question again. When you see a theorem, you convince yourself it is true. Why are convergent sequences bounded? Well, okay, I'm going to concretely, let's say I have a sequence converging to 0. How do I know that it's bounded? Well, eventually all the terms will be small, right? That's what converging to 0 means. Past some cutoff point, all the terms are small. So those terms will all be bounded. Past a point, you can bound infinitely many terms at the same time by the convergence. And then you only have finitely many terms left at the start. And a finite set is always bounded. So the idea is that because of the convergence, because of things getting small, you can bound infinitely many terms at the same time and be left with a finite problem. And that's that makes us expect that, any converging sequence should likely be bounded. And there was also nothing special about 0 there. Well, I said the terms are getting small, but instead of saying they get small, you can just say they get close to the limit, and you're still able to bound them. So that's our intuition. How do we translate this to a proof? Well, again, the proof comes from the intuition. We're going to let AN converge to A. There is some big N so that beyond that cutoff, the distance between AN and A is smaller than 1. Now, just if you go to a number line mentally for a second, if the distance between AN and A is smaller than 1, then AN must be smaller than A plus 1. Because if AN is further off to the right than A plus 1, then it will be a larger distance than 1. And the reason we can do this is by convergence, we can make the distance smaller than epsilon for any epsilon. I just picked epsilon equals 1, which I'm allowed to do because I am told that this sequence converges. Because I'm given the sequence converges, I have a for all in my hypothesis, so I can pick my favorite epsilon. To be very clear, you can't pick the epsilon when proving convergence. You're proving the for all. But when you're given convergence, you're given that it holds for whatever epsilon you pick, whether that epsilon is 1, a million, 0.0001, or like 1 divided by pi squared, it doesn't matter. So I can make an smaller than a plus 1 for all n past my big cutoff point. And this means that I have bounded infinitely many terms of the sequence at once. And so I have that the sequence is bounded by the maximum of a1 through a big N and then a plus 1, because these first big N terms bound the first big N terms of the sequence, and this last term bounds all the rest of them. So in this way, we have taken our intuition about this, and we've translated it into a proof using the formal definition. And this is something that holds for all sequences. Now, whenever I hand you a convergent sequence, you can hand me a bound for it. And this is an immensely useful tool that we will actually be using in the next lemma. Now, this is really important because the next proof is much harder than this. So I want everyone to think for like a minute or two. Do you have any questions about this? Do you actually sincerely? Yep. Oh, yes. You are correct. For the bottom, you would use a min, and then you would do a minus 1 there by the exact same logic. Because like the distance between an and a being smaller than 1 also tells you that an is bigger than a minus 1. So there you can bound infinitely many terms at once from below. And then, yeah, you're right. I should have mentioned that. But you can bound the infinitely many terms from below. Then you take a minimum across the first n terms, and you get your lower bound. That makes sense? Awesome.
Yeah.
Right. So here in my hypothesis, I am assuming that an converges. What is the definition of that? The definition is that for any epsilon greater than 0, there exists an n so that blah, 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 blah.
Yeah, also, the hypothesis is not currently on the screen.
Oh,
but
yeah.
it was in the
No,
previous.
it's right here. Let an converge to
Oh,
A.
okay. Sorry. Yeah.
So because I am assuming that an converges to A, by definition, this means that for any epsilon, you can find an n such that, if absolute value an minus a
And if
is less than epsilon for n past n, which in particular means I can do it for any specific epsilon, right? Like if I can do it for all epsilon, I can definitely do it for epsilon equals 1. But when you're proving a sequence converges, it is up to you to prove the for all, right? You are being asked to show you can do something for all epsilon. And so if you pick a specific epsilon, if you're showing a sequence converges and you only show it for epsilon equals 0.5, you haven't shown this for all epsilon at all. You've shown it for one specific epsilon, but that's not what you were asked to do. So the difference is whether you are trying to prove a for all epsilon statement or you are assuming a for all epsilon statement. If you're assuming for all epsilon, then of course you can use a specific epsilon. If you're proving for all, you actually need to prove it for every single one. That makes sense? Awesome.
Yeah, and if you don't like that kind of quantifier stuff, like for all, think about it like if it gets really, really close, I'm like, oh, hey, like these sequence gets really close to this number. Well, does it get closer than a distance of 1? Well, yeah, gets any close I want, right? So it gets as close as you want thing, which is important. That's why we have the for all epsilon. And if you're anything like me when I was starting it, you might get scared of that upside down A and that upside down E. But you're gonna get intuition for that also at some point. But the upside down A, which means just for all epsilon, I think we avoided using those in writing. Okay.
So for all is like terrible mathematical shorthand. Professors use it on the board because it's faster to write. That's it. That's how those like symbols started. Use words when you can, they're easier to read. Okay. This proof is done. Let's go on to the product proof. So the product proof is a lot harder, and the reason it's a lot harder is it's kind of unclear what to do. Like, who here actually tried proving this when they read it in their 137 notes? Okay, well, all of you should raise your hands. When you hit, like, I get that you didn't, but when you hit new theorems, spending even 10 minutes trying to prove them is very valuable. And if you try to prove this one, you'd notice you're trying to make product an bn minus product ab small. And that's really hard because the only conditions you have are on an minus a and bn minus b. And if you don't have that anywhere. So this theorem is not immediately easy to approach, but there is a clever trick. And Zev kind of is going to talk through the solution. And
Yeah.
I will have more to say about the trick.
Yeah, so another thing is, like, with starting off the solution, like Nick said, it's the product A and Bn, the distance from product A and Bn and product AB. Remember that distance, the distance between two things, is defined to be the absolute value of their difference, because then it doesn't matter which one's bigger and which one's smaller. And that's why these absolute values are always going to come in when you're doing epsilon delta proofs. Or epsilon, sorry, I'm getting ahead of myself. When you're doing proofs involving epsilon. So it is almost like a triangle inequality for products. And we also know that when we have absolute values, we like to use triangle inequality to make things easier. So we have this right now. We start off with this. This is the distance between A and B and AB. And we want to prove that distance gets really small. We want to prove that for any epsilon, I'm just going to take, any epsilon, I can find a big N that makes that really small, right? And it's hard. You might be thinking, how am I going to do this if I don't have exact numbers? Like, you can't just let N be 4 over epsilon plus 1 here, because you're going to run into problems. But let's first figure out what to do here. So the first step is to add and subtract this term. I know that seems a little weird, but if you are experienced with, like, factoring stuff, this might look a little familiar in that we're trying to kind of factor it by a group. So we're trying to get stuff that we like, because when we have things multiplied together, sometimes that makes things hard, because generally dealing with the sums of things is easier than dealing with the products of things. That's a very general statement, but it tends to be true. And I see that, I only have one AN here. What the heck am I going to do with that? And I only have one BN, and I only have one A, and I only have one B. So adding and subtracting this term, Nick, do you have anything else to say about the intuition for adding and subtracting the term there?
Yeah, so this trick, remember when I said our triangle inequality? Like, the intuition for it was if X is close to Z and Y is close to Z, then X is close to Y. So here our X is A and Bn, and our Y is AB. And if you sat down and tried for like 10, 15, 20 minutes to just work with this directly, you would not get anywhere. It's really, really hard to do this proof directly. So you would say, I am having trouble showing that X is close to Y. I am having trouble showing that two things are close to each other. Let's see if there's a middle thing that they're both close to. And kind of there are natural choices for the middle thing they're both close to, which is just to replace one of these sequences with the limit, because obviously both of them are going to be close to that. The reason that like ANBN is going to be close to ABN is that A is close to AN, right? And the reason that AB is going to be close to ANB is that AN is close to A. Mm-hmm. And so we found kind of a central point that's close to both of them. Now, very important, at this step, we do not know that this trick is going to work. When you are writing solutions, it is okay to try things that might not work out, that don't necessarily make sense. But this seems like a good guess because it is close to everything involved, and because if you kind of take a couple more steps, you'll start to get something that looks very promising. Mm. So that was how, like, I didn't look up a proof for this. I wrote the proof of this slide based on what made sense to me, just off the top of my head. And this was how I thought about it.
Yeah. And I'm going to skip ahead one step to... yeah, actually, I'm not going to... yeah, okay, so I'll reveal this step. So this step is where we use the triangle inequality. And... okay, the way I write this might be a little bit different. But if you notice, if you try and go a step back from this last bit, if I take this AN and multiply this there, I get ANBN minus ANB, right? And here I get ANB minus AB, right? Taking the B and multiplying it in. So yeah, we have this ANB that's close to both the things. The other reason why is if you really like you might like the intuition, but you also might like seeing the numbers on the paper or the screen or wherever. So what do we have that we can use? We know that AN converges to A and BN converges to B. So what you want to try and do is use the definition of the limit to prove that this is the limit, right? Which makes sense. In order to prove that something's a limit, you want to use the definition of a limit. But what does the definition of a limit have that's really useful? What has the distance between AN and A? We know that distance gets small. So one way of thinking about this, and remember, the intuition is also important, but when you're manipulating equations and you want to try and figure out intuition, okay, how do I manipulate this equation? I want to find the thing that I like to work with. So if I'm manipulating an equation, and I know from here, from the start, I don't know what I'm going to do with this, but I know that an minus a and bn minus b both get really small. So I want to make those things appear in my equation by manipulating it, right? So manipulating it to try and get something to appear that you know how to work with is probably one of the most important parts of manipulating equations, because it's not like when you're simplifying, you're not trying to do that. You're just trying to crunch stuff down, which is probably the majority of the equation manipulation you did in high school. Or when you're trying to isolate a variable, you know your thing is already there, your variable's there already, you're just trying to isolate it. This kind of manipulation of equations is different, and it requires this step of what am I looking for? You have to think of what you're looking for and think of how to try and get that thing. And if I'm looking for bn minus b, well, I already have a bn here, and I already have a minus b there, but I don't think that's going to be the same bn minus b that I'm going to end up with. So if I take a bn there, well, if I want a minus b, I have to do something about this an. So my term that I'm putting in has to also have the an. So that's why I put in the minus a and b. And obviously, if I minus it, I have to add it also so that my thing is still equal. And then look, I'm noticing on the right side now, I have this b that I can take, that I can factor out, and then I have my an minus a. So when you do something that to try and get one thing to work and it also gets the other thing to work, that's a good sign that you're on the right track. So then we do end up factoring up these terms, and then we use the triangle inequality. There's a little here we're technically using the version of the triangle inequality. This thing on the left plus this thing on the right, the absolute value of the sum is less than or equal to the sum of the absolute values. But you could also directly use the definition that we wrote by making this a and b be the z term.
Yes.
Yeah. So continuing from here. Oh, okay. Yeah. So now we're going to use. Do you want to continue?
Yeah. So now we get to use like our lovely little thing from before. Kind of a nice thing is that like about actually I'm gonna go back a step and just talk about why we're not immediately done. If the things in front of bn minus b and an minus a were constants, we would be immediately done. Because we can make an minus a as small as we want. So we can make it smaller than epsilon divided by a constant. So the big issue with the current form of this is that absolute value of an depends on n, right? And so this means that like the big N we pick for the epsilon might not end up working out, because what if for like a larger value of n we have a problem or whatever? So we want to find a way to make this coefficient no longer depend on n, because then we can just pick a single value of big N that'll work no matter what. Well, that'll work for the given epsilon. And this is where our proposition comes in. Convergent sequences are bounded, right? We do not care about equality here at all. We just care about making things smaller. So the absolute value of an is a convergent sequence, which means that we can bound it above by some number m. And the next step is literally just to bound that inequality. To throw that in with that inequality. Because this now gives us an minus a and bn minus b with just constants in front of them, right? Like no matter what b is, for this question it is a constant. And no matter what m is, for this question, it is a constant. And now we can pick a sufficiently large n so that bn minus b is smaller than epsilon over 2m. I've been sloppy with my quantifiers here. Let's pretend that we were handed an epsilon. So like at the start, if I had said, let epsilon greater than 0 be arbitrary, we could pick a big enough n so that bn minus b were smaller than epsilon over 2m, and an minus a were smaller than epsilon over twice the absolute value of b. And then if we just look at like this thing above, we would get, m times epsilon over 2m. So this would become epsilon over 2 plus another epsilon over 2. So we would have this an bn minus ab being smaller than epsilon.
Mm-hmm.
And I have a comment here. Why were we allowed to do the last step? This is something a lot of students get hung up on. They go, well, I can only make bn minus b smaller than epsilon. Why did you make it smaller than epsilon over 2m or whatever? This is kind of a legacy of notational overload. What's been going on here is that bn minus b can be made smaller than any positive distance. The letter we use for that distance is epsilon, but if there's another epsilon in the question, this doesn't mean that bn minus b is only smaller than that specific epsilon. Bn minus b can be made smaller than any positive number. And if we are handed an arbitrary epsilon, epsilon divided by 2 times m is in fact a number, right? And so we can make bn minus b smaller than that. And similarly, we can make an minus a smaller than whatever else. I should also note, I have not put casework in here for either m or the absolute value of b being 0, but in those cases, there's kind of a very easy modification you can make. And I felt that like getting bogged down with the details was not worth it, because the question is not about intricate casework, right? The interesting thing about this question is this trick where we added and subtracted something that was close to both, because this was both algebraically useful and like pictorially intuitive. That's the interesting part of the question. So like if they ask you this question in the final, which I really don't think they would, but if they do and you forget the casework, don't be like, oh, the review session told me. No, I'm telling you we missed casework, but you can fix the casework.
There's one other thing that I want to mention here. And it's the fact that, see, we're saying we're making bn minus b smaller than that, but if you remember back to the definition, there was a big N somewhere, right? We had the idea of this cutoff point. So is it true that this distance will always be less than whatever epsilon we want? No, you might have to go really, really far down my number line. I might have to get a really big N, right? So we did go over that, but I wanna say for a sec also because it comes up here. So here, I know that there is a sufficiently large N, which I'm gonna call N1, right? That'll make this smaller than epsilon over 2m. So I know there's a cutoff point where this will always be smaller than that. I also know there's a cutoff point where this will always be smaller than that. So I have these 2 cutoff points. And one thing that also might trip people up is, what if those 2 cutoff points are different? How do I know that there's going to be a common cutoff point? Well, you just take the two cutoff points, and whichever one's bigger, because the whole thing is that it's whenever you're bigger than the cutoff point, then you're good. So if I have a smaller cutoff point for this and a bigger one for this, I can just, the bigger one's a cutoff point for both now. So whenever I'm bigger than that biggest thing, I'm all good.
Yeah, this is a theme we'll see later. When doing epsilon delta proofs, minimums will let you combine restrictions. When doing sequences, maximums will let you combine restrictions.
I know that there is definitely, again, a lot of numbers, but it's it's most important that you understand the intuition. So instead of saying, I started saying like big N1, forget about that for now. So instead of thinking of it, oh, there has to be a big N, think of it as, well, there's a cutoff point after which it gets bigger. And if I have 2 cutoff points, I can just go past both of them and make that my new cutoff point. So if you're having trouble understanding like the direct notation and you feel like that's hurting your understanding, use the conceptual part when you're trying to understand things.
So we have a beautiful theorem here called the monotone convergence theorem. This is a wildly ludicrously important theorem that, as far as I know, in 137, you basically just use to prove that recurrences converge. But it is still an important enough theorem that I feel like it's worth mentioning. This says that if we have a bounded sequence that's monotone, then it converges. And everyone remembers the definition of bounded and monotone, right? Yes, no, maybe so. Speak now. Yeah? Yeah? It does, yes. Because keep in mind, there's also a factor of m right here. The whole point is the factors of m cancel with each other. Because we made bn minus b smaller than epsilon over 2m. So m times epsilon over 2m just leaves you with epsilon.
Yeah. If you were proving this rigorously, you'd continue this inequality string a little bit. You'd say, okay, since this is less than that, that's less than that. This whole thing is less than m times that plus absolute value b times that. And then your stuff will cancel out nicely and you'll just be left with an epsilon by itself. Yeah. Yeah. You'll have, yeah. Not necessarily.
All we're saying is that m times epsilon over 2m plus absolute value of b times epsilon over 2 absolute value b is smaller than epsilon. That's all we're doing here. Right? Because the goal was to show that bn minus ab was smaller than epsilon.
Because the important part is the m's will cancel out.
The m's will cancel and the absolute value b's will cancel.
So even if they're both big, they'll cancel. If they're both small, they'll cancel. And it won't matter that we've multiplied by m because we're dividing by it again.
How do we know? Because we can choose, remember that AN converges and BN converges. So for any positive distance, whatever it happens to be, we can pick a cutoff point where beyond that cutoff point, the distance BN minus B is smaller than this, right? This is the whole point. We can make this as small as we want. We can make it smaller than epsilon divided by 1,000,000. We can make it smaller than pi squared over 6. We can make it smaller than literally any positive number. And so I picked the positive numbers that made this proof work out. Because when you have a converging sequence, you can pick a cutoff point where the terms get as close as you want, no matter how close that is. Yeah, good, awesome. So yeah, back to fun theorems. Monotone convergence. This is a shocking, like this is a very intuitive theorem that often doesn't get presented that way. Most people have tablets. Okay, that's good. I might get you to draw something at some point. But here's the intuition I picture. Let's pretend I have an increasing sequence and I'm plotting the points. And like my arm is an upper bound for the sequence. So I might plot a point here and then here and then here and then here. Ooh, I should probably lower this a little so I can keep it horizontal. Here and then here and then here and then here. And the idea is that at some point, your dots will get squeezed between your upper bound and the previous dots. So kind of you get sandwiched and your terms eventually have to be close together. And like for a sequence, if the terms are eventually arbitrarily close, clearly they're converging to a limit. The monotone convergence theorem is powerful because it allows us to conclude things about the convergence of a sequence without making any gross epsilon computations, right? Because all you need to do is show that your sequence is increasing and bounded, and then monotone convergence will allow you to, sorry, not increasing, monotone and bounded. And monotone convergence will allow you to conclude convergence without using any gross fact at any point. You won't need to do like this kind of disgusting computation if your sequence happens to be both monotone and bounded. And kind of just the one thing that I feel is worth mentioning is that this is really, really useful for recursive sequences. And the reason is that recursive sequences can be proven to be increasing and bounded incredibly easy inductively. Now, for those of you who were not here for the 135 session, induction is like tailor-made for recurrences, right? Because the nice thing about induction is it allows you to reduce a problem to a previous case of the same problem. And recurrences define a sequence in terms of previous terms of that same sequence. So what this means is that if you have a recurrence, doing inductive proofs of like being monotone or of being bounded are often completely trivial. And once you've done those easy inductive proofs, you can just use this theorem with like no further computation to show convergence. We're not going to go through any problems for these because they're kind of all very rote and similar. But if you guys really want us to go over one during the Q&A, we can go over one on the Blackboard. Okay, before we get to functions, I'm just gonna give everyone a like 5-minute breather because we've done a lot of stuff, and then Zev can get us started on functions. Get some water, shake out, go to the bathroom if you have to. And at what time is it? At 5:05, we will be starting again with stuff on functions and limits and continuity.
All right. Going good so far.
Going great so far.
Yep. I'm gonna take a breather also.
Yeah. The slides will be uploaded. If you still want a picture, I'm happy to go back, but yeah. Wait, which one? Oh. Yeah, then it's bounded.
This is why you pick like big arrows.
Yeah, because of this, I was able to guarantee the existence of a big M. The reason I picked the big M is I wanted to get rid of the dependency, right? Because kind of we need the smaller than epsilon to happen for every single. Exactly. Because if it's not a constant there, then it could change for different M's. But like the definition is to look for all M beyond. So replacing it with a constant makes my life way better.
Oh, it's like M is the limit.
M is the bound. It's the upper bound. It's not necessarily the limit, but remember that the previous thing we proved was that it's bounded. Yeah. No problem. No, no.
Is the Q&A gonna be like 9?
The Q&A, I depends on it. Yeah, yeah.
I'm gonna go pee and then we can start again.
Yeah.
Tell Nicole that you're doing fantastic and I'm very better than and you're gonna gold sticker.
Yay.
All right, get back to your seats. We'll be starting in like a minute. Also, there will be pizza at the end once we are done lecturing. So make sure you stay because I like lecturing to a room of people and you guys like getting pizza. I did not know there was pizza. Actually, sit down. I'm very tired. It's okay. We're doing great, and we've got like we're about a third of the way through. That's ideal. All right. Shut up! Wow, you guys are way less good at it this time. Everyone, shut up! There we go. You guys did better there. Okay. So, we're gonna be going through a lot of our stuff with functions now. We will be doing fewer problems for functions because kind of the approach to an epsilon delta proof and an epsilon n proof is nearly identical. But there are some special things about functions that are worth mentioning. Then we'll kind of get into the real meat when we talk about IVT, EVT, MVT, derivative stuff, and we'll end it off with some Taylor series. So, functions. Do you want to take this, Zev, or should I?
Yeah, sure, I'll take this. So here's the function definition of a limit. You know, we're starting with this definition right off the bat. The limit as x approaches a, so we notice we don't have a thing approaching infinity anymore. It's not getting like, it's not zooming down the number line. It's getting really, really close to a specific value. And that limit is L if for all distances epsilon greater than 0. So far the same for all distances epsilon greater than 0. There's a distance delta greater than 0, so that if 0 less than absolute value x minus a less than delta, then the distance between f of x minus L is less than epsilon. It's a very similar idea. I've added a picture to help, but I'm going to first explain why this definition is really, really similar to the sequence definition. So the picture might help. So with the sequence definition, we also had this L plus epsilon, L minus epsilon thing going on. And we saw that eventually the sequence, as you go far and far down the number line, has to get to within these dotted lines, right? It has to go within these horizontal lines. But now I want x to be approaching a. So now, instead of saying, but before for the sequences, we have this idea of a cutoff point big N, right? That cutoff point big N plays the same role as this cutoff distance delta. So the big N, when I say for all n greater than or equal to big N, what I'm saying is for all n that get really close to infinity, right? The being bigger than any certain value can be thought of as getting closer to infinity. And similarly here, when this distance x in a gets smaller than delta, x is getting closer to a. And so the delta plays the role of the cutoff point. Just like how making your epsilon closer together means you might have to take a bigger cutoff point before it's close, putting these epsilons closer together means I have to make this delta smaller in order to make sure that it's close enough that it's also close between the epsilons. And there's also one other thing I want to point out. This 0 less than absolute value x minus a. That part is important because what it says basically, if that 0 less than wasn't there, then the distance between x minus a could be 0. But that would mean we're considering when x is equal to a. And by definition, when I take the limit as x approaches something, I actually don't care what happens when x is equal to that thing. That doesn't affect the limit. That's totally fine to just do whatever it wants. You can completely go off the rails when x is exactly equal to a. All that matters is as x gets close to a, you're good. It's sort of the same way that with a sequence, you can never have your n equaling infinity. It can just get close to infinity. So we're sort of artificially putting that here by saying x is never going to equal a, but it is going to get close to it.
So yeah, I just wanted to mention that like there are also concrete reasons to do this. This is not arbitrary. One of the classic ones is the definition of a derivative, because when you do the derivative definition, if the absolute value, like if h equals 0, the derivative expression makes no sense. It only makes sense for h which are not equal to 0. And kind of this is one of the points, you can take limits towards points where your function is not defined.
Mhm.
And one of the the classic application of that is derivatives, but we do this all the time. And so by putting that flexibility into the definition, we A, capture only caring about approach, and B, are allowed to approach points that are not in the domain of our function. And this is really, really helpful and kind of the fundamental thing that makes derivatives work. So I'm going to just go through one quick abstract proof. Fun fact, this was on either the 2020 or the 2021 final for Math 137, which means that this question is something that you could have reasonably seen on your exam. Just like to be clear, this is the actual like difficulty and style and whatever of questions that have historically appeared on 137 exams. Will it appear again? Definitely not, especially not because the prof sent this to me, but like a similar question might. So knowing how to do these is not only important for understanding, it's important for the final. So assume that our limit as x goes to 4 of f of x is 7. Show that the limit of f of x squared plus f of x plus 1 is 57. What's the first thing we do when we see a question? We convince ourselves it is true. So the whole thing here, the whole shtick is that if f of x is approaching 7, then like f of x squared should be approaching 49, and f of x should be approaching 7. Well, no, is approaching 7.
By the way, there's an x approaches a there. That should be an x approaches 4.
Oh, that should absolutely be x approaches 4. Yes, my apologies. First typo. Whoa. So 49 plus 7 plus 1 is in fact 57. So this is like saying, okay, the obvious thing happens. And on the exam, it was stated as a like, you can't use any of the limit rules from chapter 2. You have to only use epsilon delta. So that's how I'm going to do it. What is the first thing we do? We manipulate this expression, the distance between, the function we're working with and the limit, in a way that makes sense. And here, I've turned this 1 minus 57 into like a 49 and a 7 separately. And the reason I'm doing this is, intuitively, we expect f of x squared to be getting close to 49 and f of x to be getting close to 7. So what I'm going to do is I'm going to triangle inequality this into two different terms and then focus on making both of them small. So this is, less than or equal to. I've just applied kind of the one version of the triangle inequality here. And then what I notice is I can factor f of x squared minus 49 as a difference of squares. So this becomes f of x minus 7 times f of x plus 7 plus absolute value f of x minus 7. So this is already looking really, really promising. We can make absolute value f of x minus 7 as small as we want. Kind of the only problem is the first term. This is an analogous problem to the product question we had. Because if absolute value f of x plus 7 were a constant, we'd be done. We could make absolute value f of x minus 7, smaller than epsilon divided by that constant. But f of x plus 7 is very much not a constant, right? It depends on our x. And so we can't just say, pick the delta that makes f of x minus 7 smaller than epsilon over f of x plus 7, because that changes depending on what x is. But the epsilon and the delta, the delta and epsilon you need to pick kind of need to work for all of the x's that are sufficiently close, that are at least distance delta away. So, how do we handle this? It's the same way we handled the product question. We find a way to bound absolute value f of x plus 7 from above, and then we can replace it by a constant. And once we have a constant, our life is easy and nice and beautiful. And intuitively, f of x plus 7 should be bounded because close to 4, f of x is close to 7. So f of x plus 7 should be close to 14. So we should be able to bound it above by like 15. And what this actually ends up looking like is we can make absolute value f of x minus 7 as small as we want. So there's a delta 1, so that if we make, god damn it, I put a again instead of 4. So that if x minus this a should just be a 4 is smaller than delta 1, then f of x minus 7 is smaller than 1. And then f of x plus 7 will be smaller than 15. And if you don't see how I got between these inequalities, it's just applying the definition of absolute value. This is something you can absolutely work through on your own. But once we have this bound, we can go back up and replace these inequalities with constants. And in particular, there's a delta 2, so that if x minus a has a distance smaller than delta 2, then the absolute value of f of x minus 7 is going to be smaller than epsilon over 30. And then when we replace all of the bounds, we would have epsilon over 30 times 15 plus epsilon over 30, which is certainly going to be smaller than epsilon. So in the and we pick delta to be the minimum of delta 1 and delta 2 because we want both of these restrictions to happen at the same time, right? We want both f of x minus 7 to be smaller than 1 and f of x minus 7 to be smaller than epsilon over 30. And just as how in sequences we pick the maximum of n1 and n2 to have the limit towards infinity get like both restrictions, to get both restrictions on absolute value f of x minus 7, we pick delta to be the minimum of the two deltas. Because if you're smaller than the minimum of delta 1 and delta 2, you're smaller than both delta 1 and delta 2 individually. And so both of these restrictions will apply. This is why a lot of the time these epsilon delta proofs will involve taking a minimum somewhere. It's because you want to get two restrictions going at once. You want to, for example, bound f of x plus 7 and f of x minus 7, and minimum is how we get both of the restrictions at the same time. Does anyone have any questions about this proof? Yeah?
Elaborate on how you get absolute value of f of x plus 7 is less than 15.
Yeah, absolutely. If absolute value f of x minus 7 is smaller than 1, then the biggest that f of x can be is 8. And so adding 7, the biggest it can be is 15. This is easy if you picture a number line, right? If you draw a window of size 1 around 7, this like first condition would tell us that f of x is between 6 and 8. So f of x plus 7 would be between 13 and 15. So it's certainly smaller than 15. This is one of many, many reasons that being able to think of absolute values as distances is incredibly helpful. Because doing that algebraically, like it's not the easiest thing in the world. But if you have this picture in your mind of, you know, this interval around 15 or around 7, it immediately follows. All right. Anything to say about that, Zev?
No, I don't think so.
Awesome. Oh, you had a good picture for squeeze theorem,
Yes,
so I'll let you take
I had two good pictures for you soon. So the next thing is squeeze theorem, which you've probably heard about. It basically, the idea behind squeeze theorem is you have three functions. I know it's a lot, but bear with me. So three functions, and you have your function g, and my function g is my very, very bad function that I want to bound between things, right? It's my function that I'm trying to find the limit of. It is the important one here. These f of x and h of x are kind of utility functions that we're going to use. But first, let's just get to the theorem. So if the limit of as x approaches a, I'm going to stop saying that part, but if the limit of f of x equals the limit of h of x, and g of x is between them, then the limit of g of x exists, and it's equal to the other two limits. So I have some pictures here. So it's useful when you have a bounded function that's poorly behaved. So like sine x over x, and this limit as x approaches infinity of sine x over x, that's actually this function, except it's as a sequence instead of a function, but that doesn't change anything. So I can see in this picture, I'm having my x get really close to 0, and I have this oscillating function here. This is like sinusoidal wave function. That's my g of x, right? And if I look at this and say, like, clearly, ignore the red and blue for a second, this function does really get really close to 0, right? But if I were to try and prove using equations that it gets there, I would run into problems because I'm, you know, like this is not a very well-behaved function. It might not even have a nice mathematical formula. So I want to bound it between these two functions. And since these two functions, they go to 0, the function between them also goes to that. And this kind of is a very similar intuition, like the intuition for why this is true. It's sort of similar to the intuition why the triangle inequality is true. The triangle inequality is if A gets close to B and B gets close to C, then A gets close to C, right?
Yeah.
So if I have two things that are getting really, really close to a limit, a thing in between them, it can't be further from the limit than either of the other things because it is strictly between them. The limit is always, like, it's always going to be in between them, and the limit's also in between them. They're also approaching the limit. And then this other picture on the right shows an example where instead of x approaching a specific value, my n is approaching infinity. And this is kind of a very similar thing. And it also, I think, helps illustrate that function limits are very similar to sequence limits as well.
And I'd just like to explicitly talk about how we squeeze sine x over x. We squeeze it between -1 over x and +1 over x. Because sine x is squeezed between -1 and 1. So dividing through by x, -1 over x less than or equal to sine x less than or equal to 1 over x. And the point here is that by replacing sine with constants, it's so nice. We completely kill the oscillating behavior. And then we just have a constant over x, which clearly goes to 0, and another constant over x, which also clearly goes to 0.
And this is also, this technically is like sine x over x plus some constant. But if you imagine the x-axis gets kind of moved up to here, then it's just
Yeah,
sine x over x.
And that's exactly, this picture shows it, right? The first line and the second line are clearly translated versions of 1 over x and -1 over x. And sine x over x is sandwiched between them. So as you go off to infinity, the limit's going to be 0. Yeah? The second picture is x to infinity. And yes,
You just want the x approaching 0.
the sine x over x as x goes to 0 is not, you can also do that by squeeze theorem. The squeeze theorem's a lot less trivial there.
Well, this isn't sine x over x, this is different.
But sine x over x as x goes to infinity, that's the second picture here. And yeah, that one follows immediately by squeeze theorem with the bounds I talked about. Awesome. Next slide.
Yep.
Oh
Yeah.
yeah, we're right. That's kind of the
Yeah, so when you, I guess we talked about why squeeze theorem is true, but I guess another important thing to talk about is why am I going to use it? Not everything that's true is useful, but squeeze theorem is useful because, you know, G might be poorly behaved sine function. I guess we did kind of talk about that. But squeezing about constants, the way we do that with sine functions, you're going to see squeeze theorem a lot. I'd say like 90% of the time you see it, it's with sinusoidal functions.
yeah.
And that's because the really, really nice thing about sine and cosine functions is that they're bounded by 0 and 1. If you look at a sine wave, you know that the sine wave, regardless of how far it goes, even though it keeps going up and down and up and down, it's always going to be less than or equal to 1, and it's always going to be greater than or equal to -1. And that's how you can bound it between constants.
Mm-hmm. Yeah.
So yeah, I want to talk about continuity. Continuity, I am not going to spend any time on with problems because continuity problems are the same as limit problems. Like intuitively, we all know what continuous functions are. You even maybe had the high school definition of you can draw it without lifting your pencil, which is not a terrible definition, but it's hard to work with. And it's hard to work with in the abstract setting, right? What is it? If I can draw F without lifting my pencil and I can draw G without lifting my pencil, how can I draw F plus G without lifting my pencil? Like, it's good to have that picture, but it's also good to be comfortable with the formalism. So there are two equivalent like definitions of continuity. The first one has a lot of epsilons and deltas. And I know I said epsilons and deltas were bad form, but when I put the words, it didn't fit on a single line and I wanted a single line. So there's the, you know, for all x, for all epsilon, there's a delta, so that if the distance between x and y is smaller than delta, then the distance between f of x and f of y is smaller than epsilon. Or there's the much more compact. For all a, the limit as x approaches a of f of x is f of a. Now, very important, these two definitions are the same. If you take the second one and you unfold the epsilons and the deltas, it becomes the first one. But intuitively, they say two different things. What the first one says is that no matter where you are, if you change your input by a small amount, a sufficiently small amount, then your output only changes by a sufficiently small amount. What the second one says is that as you approach a point, the value of the function is the value that you were approaching. These are both like good ideas to have, and I would recommend being comfortable with both of these. Either small change in input leads to small change in output, or what you approach is the actual value at the point. You will work with both of these, but like doing this is literally the same as doing an epsilon delta limit proof, so I think there's no reason for us to go over it. If you guys disagree, you can ask us during the Q&A at the end. We can do some on the Blackboard, but like, yeah, they are the same.
I do want to say one other thing about this.
Yeah.
So, just to help you make sense of this top one a little more, notice that this absolute value x minus y less than delta part, it looks a lot like the thing from the definition of limits of functions, except we got rid of that 0 less than absolute value x minus y. And that's because, again, we had that 0 less than absolute value x minus y, so we didn't have to worry about when my things are equal, only about the limit. But here, since we don't have that 0 less than, taking that away, like what that means is that it's the same, except we also care about what happens when the things are equal, which is why we're not just saying this limit exists. It has to be equal to the thing when x is equal to a. So yes, x has to, when x approaches a, that's to like approach some nice value. That value has to be the value f takes at that point.
So the main, actually, one last thing I want to say, and this is something you will see over and over and over again in math, is often the functions we care about are the functions that quote unquote preserve nice properties. So next term, all of you will take Math 136. Some of you in Math Phys are already taking it. And in Math 136, you learn about these things called linear transformations. And linear transformations are a special kind of function that keeps straight lines straight. If you go on to take PMath 347 or 348 or whatever, you'll learn about things called homomorphism, which is a big fancy word. But kind of over and over again, we care about functions that preserve nice properties. In calculus, the fundamental thing is distance. This is what we care about. Everything we've done so far has involved distance. So it should make sense that the functions that behave nicely in calculus settings are the ones that in some sense respect distance. Continuous functions, you can't have an arbitrarily small change in the input leading to a jump in the output. And this is good and this is nice, and this works with what we want our functions to do. Good theorems, intermediate and extreme value theorem. I'll take intermediate, or I'll take extreme, you take intermediate?
Sure.
Awesome. So if we let f from a closed interval to the real numbers be continuous, then f has a max and a minimum. That's what this says. I've written out having a maximum and a minimum in more important terms, in more like formal terms. But what this says is a function on a closed bounded interval attains a maximum and a minimum. And I think the best way to get intuition for this is to think about functions that do not have maxima or minima. So a first good example of a function that does not have a maximum or a minimum is 1 over x on the open interval 0, 1. And the reason that doesn't have a maximum is that it's unbounded, right? It blows up to infinity. Another kind of obvious example is the function x on the open interval 0, 1. It doesn't have a maximum because, like, let's pretend I say the maximum is 0.9, and you go, well, no, at 0.99, it takes a value 0.9, and I go, well, that's the maximum. You go, no, at 0.999, it's bigger than that, but at 0.9999, it's bigger than that, and so on. You can always find a bigger point. And similarly, again, on the open interval 0, 1, the function f of x equals x has no minimum because you can always find a smaller point. If I have any point, I can just divide it by 2 and get something smaller. But if I like take that function and I fill in the endpoints, you know, I draw the point at 0, I draw the point at 1, I get my minimum and my maximum. And that, like, you know, I get the minimum at 0 and the maximum at 1. And kind of the point of this theorem is that a function on an open interval will fail to have a maximum or a minimum if the maximum or minimum, quote unquote, should be at one of the endpoints. Like f of x equals x, the maximum should be at the endpoints of an open interval. The open interval doesn't contain its endpoints though, so you don't achieve the maximum. On the closed interval, you put the endpoints in, so you actually hit the maximum. The reason for requiring the interval to be bounded is essentially the same. It's that you could have a function like arctan x, which kind of looks like this, that has a horizontal asymptote that it never touches. And the issue with the horizontal asymptote it never touches is it should have a maximum at infinity, but there's no point at infinity, so it doesn't hit its maximum. In like every single case, we see functions without maximums. The issue is that they're missing their endpoints. So it should make sense that when we put the endpoints in, when we have this nice closed and bounded interval, we actually get our maximum and we actually get our minimum. Now, the proof of this is substantially more sophisticated than anything you do in 137, very unfortunately. I think this is a beautiful theorem to prove, and they do prove it in 147. If any of you are interested in getting a proof of this theorem, it can be proven using the monotone convergence theorem, and I will happily go through that like in the Q&A, but it's not something you need to know. This theorem is super useful. You guys had a midterm question that used this that I think people had some trouble with. I heard that it didn't go great, but I will be going over that question in a couple slides. Was it question 6?
Yeah.
Yeah? Okay, I will be going over question 6 of your midterm in like a slide, but first let's talk about the intermediate value theorem.
Well, because 2 theorems back to back is a lot, does anyone have any questions about the extreme value theorem?
Oh yeah, that's a fantastic question. Anyone have questions about this? Awesome. Then I will do question 6 after Zev takes the intermediate value.
All right, so the intermediate value theorem is another theorem that works for continuous functions. Oh, this is yeah. So we're having f be a continuous function defined on an interval from a to b. This again also has to be an interval in order for this to make sense. Then if there are c and d with f of c less than 0 less than f of d, there exists an x and c d with f of x equals 0. This is not the version of intermediate value theorem I'm 100% familiar with. I will go over to that also. But basically what this says is if I have, if f is a continuous function defined on an interval from, you know, a to b, if I have these things, I have my c gets into a negative number, and my d gets into a positive number. So let's say like my c is there, and here's like c and f of c, and here's d and f of d, and I have this 0 between them. This, what I'm saying is that there is some x in between them, so that f of x is 0. And the reason why this is true intuitively comes from the intuitive definition of continuity, the whole you can draw it with your pencil thing. Because if my starting point of my function is less than 0, and my end point is greater than 0, and I have to be able to draw my function continuously, then my drawing, I'm going to cross over 0 at some point. And when I cross over 0, there has to be a point where it equals 0. Now, this definition, if you sit with that for a second, you may also be able to see that it's not just about if 0 is between them. This 0 can just be replaced with any real number. So if I have a number, like let's say 5, right? And f of c is less than 5, and f of d is greater than 5. When I draw my line between c and d, right, I have to go over 5, right? So it's not just saying that your function that starts negative and goes positive has to cross 0. Basically what it's saying is if you have any value that's between two other values, your function has to achieve that value somewhere. It has to go through all of the intermediate values. Hence the name of the theorem.
And you get Zev's version from this version. If you take his example of 5, you would just subtract 5 from everything. Like f of c less than 5 less than f of d. You would subtract 5 from everything, and then you would have this version. I stated it this way because I think the going positive to negative is like the most immediately intuitive statement, and you can recover any other statement from this by just adding and subtracting appropriately.
Yeah, and we can see also like why it has to be continuous, because if it didn't have to be continuous, I could just make my function jump over the 0 and go to the next thing, which is why being continuous is important here.
Yeah. So now we've got our fun midterm question 6. Now this gave people trouble from what I hear. Did they make it a bonus question? Is that actually true? Yeah. And this problem, like, I get it, but also this problem is an immediate application, of the extreme value theorem. But it is not obvious why you can apply the extreme value theorem. So let's just kind of like, quiet, please. Thanks. So we are trying to show that some function has a maximum. What we want to do here is apply the extreme value theorem. What we want to do is say, okay, because it's a continuous function on a closed interval, it has a max and a min, take the maximum, we're done. The problem is 0 to infinity is not a closed bounded interval. But kind of just think about it for a second. The limit as x goes to infinity is 0, which means that beyond some cutoff point, f is very small, right? Like eventually f is going to be tiny. And so that's not going to interfere with f having a maximum. So our idea for this question is maybe we can restrict to just some closed bounded interval and say that because the limit as x goes to infinity of f of x is 0, outside of that closed bounded interval, f is so small that it won't affect the maximum or it won't hurt it. This is our intuition going into this problem. And here's how we make that work. So we choose some x naught so that if x is greater than or equal to x naught, then the absolute value of f of x is smaller than 1. Why can we do this? This is the definition of the limit towards infinity being 0, right? Beyond a certain cutoff point, our function can be made smaller than any epsilon. And so in particular, beyond a cutoff point, I can make the function smaller than 1. And we can now apply the extreme value theorem to this closed interval. And the crucial insight here is that whatever the maximum is on this interval from 0 to x0 is going to be a maximum of all of f of x, because beyond x naught, f of x is smaller than 1. But f of 0 is 1. So on this interval 0 to x naught, the maximum is going to be bigger than 1. And so it's going to be bigger than everything past x naught. And just, oh, I literally didn't even write that down because I just wanted to verbally say it. That's the whole point here. So we can apply the extreme value theorem in 0 x naught to get a point, let's say A, where f of A is a maximum of the function. F of A is going to be greater than or equal to 1 because f of 0 equals 1. And so f of A is greater than or equal to everything in 0 x naught by definition, right? We used the extreme value theorem to make it a maximum, and it's greater than or equal to everything past x naught because everything past x naught has the function being smaller than 1, and f of A was larger than 1. And so literally just using two definitions together, the definition of a limit towards infinity being 0 and the definition, like the statement of the extreme value theorem, we solved this problem in 2 lines plus some words. When I wrote this down, this was like 4 lines. But this problem is hard. A short problem is not, like a short solution does not mean an easy problem. The whole the lesson to take away here is not, wow, I'm so stupid for not coming up with that short solution. The lesson to take away is it was hard to come up with this short solution. And the reason it was hard is this requires a really good intuition for what it means for a function to have the limit being 0 as x goes to infinity. And on an exam, you have to apply that intuition quickly. So what you now need to do, if you did not solve this problem, is go back to it and look at their solution and look at my solution and ask, why does this make sense? And how could I have come up with it? Like, I talked through how I came up with it. I said, eventually the function's small. But how could you have? Why does this make sense to you? Yes.
So as long as like limit as x approaches infinity for some f of x is less than what it was at 0, you use like that theorem.
Yep, you can use this theorem to show it has a maximum. And that's actually, ooh, thank you for doing that. So here's another thing that you should be doing to questions you encounter, asking how you can generalize them. Our friend over there just said, hey, the only thing that we used here is that f of 0 is larger than the limit, which is absolutely true. This theorem can be generalized to f of 0 equals, let's say, k, and the limit as x goes to infinity of f of x is something smaller than k. And this would still hold true. And so, yeah.
Why do we have to have a f0 to 1 and like that the absolute volume of x is smaller than the volume of x?
So that's a really good question. The place where that hypothesis comes in, oh man, I wish I could draw on the board right now, but the board is too small. Imagine a function that like curves towards an asymptote, where the asymptote is bigger than everything of the function. So it's like curving upwards towards it. Something like arctan x. That function will not have a maximum. And kind of the place where I'm actually using this hypothesis is that I need whatever the maximum that I find in the interval 0 x naught is to bound all points in the function, not just the points in that interval. So I need the maximum between 0 and x naught to be like the value of the function at that maximum needs to be bigger than all values of the function past x naught. And I can only do that if the function is sufficiently small past x naught. So this is why I made f of x smaller than 1 past x naught, because this guaranteed that whatever the maximum was that I found between 0 and x naught, it would be a maximum of the whole function, not just a maximum of the function on that one interval. Does that make sense?
But isn't that kind of means you have to have the
Yeah, it has to have a maximum in the interval 0 x naught. I'm using the extreme value theorem for that, but the function is on the interval 0 infinity. So you're not guaranteed a maximum on the whole domain by the extreme value theorem. I'm using the extreme value theorem on this closed bounded interval to get a maximum, and then saying that maximum is a maximum on the whole domain because outside of this interval, the function is small. And if I draw, can you see this line where it's at?
Yeah.
Okay, consider a function like this. It goes down and then it goes up. And it kind of flattens off here with the horizontal aspect. This function has no maximum, right? Because over here it's bigger than it was over here, but it's increasing forever without hitting the asymptote. But what we have is that the limit, this is not what our function looks like. Our function has the limit, I'm going to just draw another x-axis over here. Our function looks like the limit as x goes to infinity is 0. So it might be really crazy for a little bit, but then it flattens out and calms down. So what I'm doing is this. I'm taking a cutoff point that's like right, and I'm saying in this interval, so this would be our x naught. In this interval, by the extreme value theorem, you have a maximum. And since the function is small beyond x naught, this maximum is larger than everything past x naught, so it is actually a maximum of the function, not just the maximum in whatever. And this requires the limit to be 0, or something smaller than the value of the function.
Yeah. The other important thing there is that just like yeah, we have a maximum. But the reason why we can get the maximum is greater than that is because we're choosing a cutoff where here it's always less than 1, right? But we know that at this point it's 1. So since the maximum is taken over this closed interval, and one of the things there has a value of 1, since the maximum has to be greater than or equal to all the things, and one of the things is 1, the maximum has to be greater than or equal to 1. Then from there, once we say, oh look, I have a maximum in an interval, and it's bigger than everything in the interval, but it's also bigger than 1, which means it's bigger than everything after it. So we prove that it's bigger than all the things.
Does that make sense?
Yes. That was, President Zero, and then you have to have a maximum on the interval, but then like, why could you just why do you have that f 0 equals 1? Like it's, I'm pretty sure.
Because if f of 0 were 0, again, if let's pretend that f of 0 were like a negative number. Yeah. So again, because you need to be able to do this, you need the maximum in the interval 0 to x0 to be larger than the limit of x goes to infinity. Because imagine our function looked like, so just going back here, and after this question, I'm going to cut you off, and we can talk more in the Q&A. Let's pretend that this were f of 0, and the function looks like this. This function has no maximum.
Oh,
So we need the value here to be bigger than the limit as x goes to infinity. So the maximum defined in the first interval is actually a bound for the rest of the function.
okay.
Good now?
Yeah.
Awesome.
Yeah.
Okay.
Right.
By the way, those were all phenomenal questions, and these are the kinds of questions you should all be asking yourselves when you read solutions. Because I am 1,000% sure that at least half the people in this room had those questions. They weren't courageous enough to ask them, but you all had them. When you are reading the solutions yourself, you need to be asking yourself, your friends, your professors those questions. You need to be writing little notes saying, why does this make sense? Why is this necessary? Etc. Because this is how you learn to do these problems. You need to be asking yourself questions.
And like an example here, like if you have a problem with a condition, so if your problem says, prove that if f is continuous, then this thing is true. Ask yourself, why isn't it true when f isn't continuous, right? Or is it not true when f is not continuous, right? And if you are able to convince yourself why your condition is sufficient for a problem, then that'll help you figure out how to use that condition. Like for the intermediate value theorem, if I wanted to prove that, I could be like, okay, why isn't it true if f is not continuous? Well, it's because my function can jump. And if that's the reason why, then I know that the way that continuity implies the intermediate value theorem, did I say extreme? I meant intermediate value theorem before, is because the function can't jump. So it tells you what properties of your condition you have to use.
All right. Next slides. So we're gonna spend a little bit of time on derivatives now. Derivatives are familiar from high school, so I'm not gonna spend too long on this, but essentially the philosophy is this. This real analysis and calculus and everything else is the study of functions, fundamentally. And we want to learn things about functions. And one nice thing about a function is how it changes. The derivative measures the change of your function. And there are lots of real world settings where the data we measure doesn't matter, but what matters is how it's changing. So one of the things obviously to talk about is that derivatives let us find extrema, maxes and mins. Zev, do you want to take extremum testing?
Yeah, sure.
Okay, awesome.
So you can finish this then.
So functions are increasing at points where f prime is positive because, again, I'm not even going through the definition of a derivative because you've all been doing this since high school. You all know it. You're taking the slope of the tangent line at a point. If the slope of your tangent line is positive, though, that means that near whatever point you're working at, the function looks like it's going up, which is why we define increasing to be positive derivative. And if the derivative is negative, then our function is decreasing. One thing that is worth mentioning is why the derivative is 0 at extrema. Why is it the case that at a maximum or a minimum, the derivative of a function is 0? This is, again, very intuitive with a picture, which I did not put in the because I had a $17,000 scholarship to apply for. Basically, the thing of this is, if I'm at a point where my derivative is positive, then my function is going up to the right and down to the left. Because the whole thing of differentiability is that whatever your tangent line is, it approximates your function well. An equivalent definition of a function being differentiable is at each point, the tangent line is a good approximation. If your tangent line is going up and your tangent line is a good approximation, your function is going up to the right and down to the left. And if your function is going up to the right, you're not a local max because it's going up. And if it's going down to the left, you're not a local min. Similarly, if your derivative is negative, you're going down to the right and up to the left. And so your function is not going to be hitting like a local max or a local min at that point. Yeah?
Is that enough to show that I'm increasing if that kind of positive?
Yeah.
Shows like x1 is like if that one is less next to like f1.
That's
So-
a different thing. Can I answer this one?
Yeah.
Yeah. So what you've described is it's actually we sort of use bad language here as mathematicians. We say increasing and we kind of mean two different things. So the thing you said, if x is less than y, then f of x is less than f of y. That's the definition for a function being increasing everywhere, right?
Mm-hmm.
That's the definition for my function, no matter how far I go, I always go up. But with the derivatives, we sort of come back to the similar notion from limits of things being really close. So if the derivative is positive, what?
So sorry, I should say if the derivative is positive in a small open interval,
Yeah.
then you are increasing on that interval.
Yeah, that's what I was getting at.
Yeah,
Yeah, so
okay.
if the derivative is positive, actually, I was going to say if the derivative is positive at a point, right? If my derivative at a point is positive, that means because the derivative is based on a limit, I'm thinking about things getting really close. So that means, you know, with the limit, with like a function being continuous, the whole idea was if I go a little bit far to the right, then I only go a little bit up. The derivative is asking, well, how much a little bit up do you go? And that is that's what the derivative is. It's if my derivative is positive, that means if I go like a little bit to the right, then I'll go a little bit up, and that means my function is increasing in a small area around that point. It does not mean it's increasing everywhere, which is a good point.
And also to be very clear here, there are functions that have positive derivatives at a point that are not increasing in an interval around that point. But this happens with very gross functions with discontinuous derivatives. With most nice functions like exponentials, polynomials, rational functions, etc., if your derivative is positive at a point, your function will be increasing near there. I haven't stated this as a theorem for that reason, though. This is just an intuition, not a precisely stated theorem. If you want the precisely stated theorem, it's in your notes. Yeah?
Yeah, so like I wanted to know what's the condition, like is it has to be strictly greater than 0 or at some points it can equal to 0 too, like at the endpoints of the interval?
Right, so that is a convention thing. Some people will say that it's not increasing unless it's positive everywhere. Some people will say it's not increasing, it's fine if the endpoints are 0. this is purely arbitrary. This is a linguistic thing. Check your notes for what applies to your course. Again, we are not reteaching all of 137. We are giving intuition. The intuition here is if your tangent line's going like this, your function's going up. So let's pretend that f prime is 0. This might not be an extremum. How do we know if it is? We'll find out.
Oh, okay. Yeah. So okay, so yeah, so you have a function where f prime is 0. How do you know if it is a maximum or a minimum or neither or both? So this is the idea of extremum testing. And these are some of these sort of tests. We were talking about tests earlier. It's important you understand the reasoning behind the tests, not just how to do them. So I'm going to just continue. If my function is a maximum, then I'm going from increasing to decreasing. And if my function is a minimum, I'm going from decreasing to increasing. So I'm going to give you a set to convince yourself that makes sense. If I have a local maximum, that means for some distance before that maximum, my function was increasing up to that point. And also after that maximum, the function is decreasing afterwards. That means that my derivative is decreasing. My rate of change is decreasing. Before this point, like before my maximum, my derivative was positive because my function was going up. And after the maximum, my derivative was negative because my function was going down. And since the derivative is a function, oh look, the derivative is positive before somewhere, and after that point, it's negative. Based on our intermediate value theorem, that means the derivative has to be 0 somewhere there. So that's how we know that the derivative is 0 at a local maximum. And it also means that we can look at what the derivative is before and after the maximum. Now, you have to be careful not to go too far before or after, because you don't know what your function is going to look like if you go really, really far. But what matters is that as long as I'm really, really close to that maximum, if I'm going to the left, my derivative is going to be positive, and if I'm to the right of it, my derivative will be negative. And if you want to, be able to guarantee that that's true, remember, we talked about the derivative has to be decreasing then, right? Or if it, or increasing, or whichever one it is. So that means we can look at the derivative of the derivative, because at a local, I guess we're doing local minimum here. At a local minimum, the derivative goes from negative to positive, which means the derivative's increasing, which means the derivative of the derivative is positive. And that's the thing there, is that the derivative isn't necessary, or it is a property of a function, but it's also a function. And that's why you can take derivatives at specific points instead of just saying, oh, it's positive or negative or whatever. And that's also why you can take derivatives of derivatives to figure out other stuff about your base function.
And remember how I said that I don't know the second derivative test? This is what I reason through every single time. Yeah?
Sorry, the functions are increasing before the maximum,
Yeah.
decrease after the maximum.
Mhm.
So we know the derivative is greater than 0, before the maximum, and less than 0 after the maximum.
Mhm.
So, but how do we know it reaches 0 at that point?
Because of the intermediate.
But that only works for continuous function. What if
That's true.
derivative is not continuous?
So
Yeah, that's a good point.
So someone has raised a phenomenal point here, which is I made an implicit assumption. If the derivative exists there, it will be 0. And the reason is derivative status. So discontinuous derivatives still satisfy something called the intermediate value property, which means that if a derivative is positive at some point and negative at some other point, it will be 0 in between. This is known as Darboux theorem. It's done in Math 147. However, the derivative could fail to exist. If the derivative fails to exist at a point, it could have gone from negative to positive, right? Like functions can, or a derivative could jump from negative to positive by not existing. Like the very classic example is if your derivative has an asymptote at a point, it could go from negative to positive. So your function could have gone from decreasing to increasing. So at critical points happen where the derivative either exists and is equal to 0 or does not exist. However, if the derivative exists as an extremum by Darboux's if the derivative exists at an extremum by Darboux's theorem, it will be 0 there. Good with that? Awesome. So classic, very easy. Well, not very easy. Here's another problem from a Math 137 final. This was on, I think, the fall 2019 in-person final. It was worth, I don't know, 3 or 4 points. Let f of x equal x to the 101 plus x to the 51 plus x plus 1. Show that it has no local extrema. This is not a difficult problem. This is kind of a quick thing. But the reason I included it is like essentially just being able to go back to a basic theorem like add an extremum, your derivative is 0, is really, really helpful, as evidenced by this literally being on the final. The solution is 2 lines. You take the derivative, f prime is x to the 100 plus x to the 50 plus 1, which is always strictly greater than 0, right? Because x to the 100 is always non-negative, x to the 50 is always non-negative. So adding 1 to this means you'll get something that's always greater than or equal to 1. So it's strictly greater than 0. This means the derivative is always positive and the derivative exists everywhere. Since the derivative exists everywhere and is always positive, it's never 0, and so there are no local extrema. Anyone have any questions about that problem? Okay, good. I just wanted to include this to be like, sometimes on Math 137, being able to solve a problem in the final is as simple as knowing a theorem. And memorizing the whole big list of theorems is really hard if you like sit down and do it with flashcards and whatever. But if you have a mental picture for these, if you can just draw them and figure out that they're true, a lot of the times rederiving a basic theorem or understanding a basic theorem enough to use it will solve huge chunks of the final for you. Mean value theorem. Zev, do you want to take this? Because you put a picture in, or do you want me to?
You can take it until the
Okay, awesome. So we have kind of the third of the value theorems, extreme, intermediate, and now mean. If we have a continuous function, which is continuously differentiable on the open interval AB and continuous on its whole domain, there exists a C with f prime of C times B minus A being equal to f of B minus f of A. Now, just for my reference, who saw this in high school? Okay. It seems like about half of you. In that case, I am going to spend some time on the intuition for this because you may not have gotten it from a high school teacher. So if we divide this expression, if we divide the f prime of C times B minus A equals f of B minus f of A through by B minus A, we get that f prime of C equals f of B minus f of A over B minus A. And what that's saying is that we have a point where the derivative is equal to the average rate of change over the interval. Now, this makes a lot of intuitive sense. The reason this makes a lot of intuitive sense is imagine that our function starts off in with a derivative larger than the average rate of change. At some point, the derivative will need to slow down to kind of make up for the fact that it was changing faster at first. So when it slows down, it will end up being slower. At some point in between, it had to pass through exactly the rate of change. Or equivalently, if your function starts off with a derivative smaller than your average rate of change, at some point it will have to speed up to be faster. And in between being slower and faster, it should be equal. Remember how at the start I mentioned that the intermediate value theorem and the mean value theorem are connected? This is the connection. This is exactly the reasoning of the intermediate value theorem. If you go from changing slower to changing faster, in between you have to be changing at the same rate. And the proof of the mean value theorem is often done by the intermediate value theorem. Now, Zev has put in a pretty picture that will kind of capture this visually.
Yeah, so here are A and B are our same points, A and B from the problem. So we see that, actually we have a few things happening here. So we see that with our A, we start from A, we're actually rising a lot faster, right? But eventually, so we're going up, if we never come back down, we're obviously never going to get to that point there, right? So our function has to come back down. Our function has to touch this line somewhere, right? But if it's touching, so here, if the function makes it back to the line, right? And if the function makes it back to the line, it's approaching the line from above the line. And that means its rate of change is less than the slope of the line. Because if its rate of change is more than the slope of the line and it's above the line, it's getting further from the line. So at this point, it's getting closer to the line, which means its rate of change is less than the average rate of change. And since it started off greater and ended off less, at some point over here, another composition shows, but it shows it happening again over here. But at some point over here even, there's a point where the rate of change is the same. And we can see the same thing happening here the other way. It starts off going down and it's below the line, but it has to come back up and touch the line.
So pop quiz here. Who in this room can tell me why the hypothesis continuous on the closed interval AB is necessary? Like, I'm not actually going to call on you, just mentally to yourself. Who can tell me why that hypothesis is necessary? Because I mean, differentiable on the open interval, differentiability guarantees continuity. So why do we require continuity on the closed interval? This was an actual question on the 2019 in-person final. Why is, like, they asked for an explicit example of a function where the continuous on the closed interval hypothesis was missing that did not satisfy the mean value theorem. And the reason is essentially what I could do is I could have a function that's like 0 at, let's let a equals 0 and b equals 1. I could take a function which is 0 at a and 0 at b, but everywhere else it's equal to just x, right? Because then f of a and f of b are the same, right? We have both of them are 0. So the average rate of change is 0, but the derivative is always 1 because our line is going up. The issue is that at the second endpoint, if you jump, the average rate of change might not actually be accurate. When you read these theorems, you should be asking yourself questions like that. Why is this hypothesis necessary? What is a counterexample if I remove this hypothesis? Because not only is this important to your understanding, they actually ask these questions on exams. And if you don't know the precise statement of theorems, if you don't understand why these hypotheses are necessary, you won't be able to do that.
One other thing, there is actually a second hypothesis here. So it's important that it's important to consider what happens if we, turn on and off our hypotheses, so to speak. So here, Nick was just explaining that if you don't need it to be continuous, then this might not be true, right? But but there's actually a second thing. Not only is it continuous, it's also differentiable everywhere. So what if it's continuous, but it's not differentiable everywhere? Will this still work? Not necessarily, because I might go like this, take a sharp turn, and then head up in a straight line to my function. And I'm not going to explain why this is true, but if your function takes a sharp turn, at that sharp turn, the derivative does not exist. So if I go like this, and then I take a sharp turn and head up like that, there was no point where my instantaneous rate of change, or my derivative, was equal to the average rate of change. But that's because it wasn't actually differentiable everywhere. So this relies on it being continuous and always able to take the derivative. The derivative has to always exist somewhere.
In terms of applying this theorem, it basically has two cases where you use it. One is when you know the derivative and you want to bound the average rate of change. We'll see that corollary next. And the other one is when you know the average rate of change and you want to bound the derivative.
Well, you can't, you're not really bounding the derivative by it, but you want to find a spot where the derivative is equal to that.
Sorry.
Because finding that point will be useful somehow.
Yeah. So this is, added a t by accident. Let's let f be continued. So same hypothesis as the mean value theorem. If you have a bounded derivative, then f of b is less than or equal to m times b minus a plus f of a. Now, what's the intuition here? The intuition here is that since m is our bound on the derivative, this expression, m times b minus a plus f of a, this is the line with slope m starting at f of a going over to b. And we're saying that since our derivative is smaller than or equal to m, the function is changing slower than this line, that it'll kind of always live below it, which makes sense because this line is increasing faster than the function. I'm not going to go through the proof in detail because this is in your notes. But what I want to point out here is that we have a bounded derivative and we then use this to bound the average rate of change. The way the proof proceeds is you assume that it's greater than, and then you contradict the mean value theorem. You find f of b minus f of a is greater than f prime of c times b minus a for all c in the interval. And you guys can go through this proof on your own. But like the crucial thing that's going on here is that we were able to bound the derivative. And intuitively, the mean value theorem gives us a relationship between the size of the derivative and the average rate of change. And this exploited that to get our contradiction. I'm not going to spend too long on this. By the way, just this by itself is a very useful theorem. I think in your notes you call it the bounded derivative theorem or something. But there were questions on of the past 3 years, 2 of the finals used this theorem. It's just generally useful to know. Okay. So this is a cute problem. And we've also been talking for a while now. So I'm going to say everyone gets a like 5 to 7 minute break. You can use the break to just break, or you can try out this problem. This was also on a past exam. This was on the fall 2019 in-person exam. Give it a shot and we'll go over the solution at 6:10.
I think that we're pretty close to being, yeah, done.
And pizza's at around 6:30 or 6:45, give or take, and we will be done talking by then.
Great. We're doing really well.
Yeah, we're doing great.
Yeah, this is awesome. We're gonna use this break. You said what, 6:10?
Yeah, so. This is, I have.
Oh, that worked less well than I hoped, but I will be going over the solution to this now. So I have so much to say about this problem because this is a cool problem, but one of the things to note is actually that this is an existence uniqueness question, right? Like if you did the division algorithm in Math 135, there was there exists a unique whatever, and you've done a few of those. You've done a few proofs where you first show that something exists, then you show that it's unique. And this is that. This is asking you to show that there exists a root and that the root is unique. And so you approach this like you would approach an existence uniqueness question. The first thing you do is just show that a root exists. And we have a fantastic theorem for showing that functions are zero somewhere. And that theorem is the intermediate value theorem. So what I would first do is note that at zero, oops, sorry. This should say f of 1 is, no, f of, sorry, we're good. F of 0 is positive. It is just equal to 1. And f of 2 is 8 minus, yeah, that's negative. So we have a positive point and a negative point. So in between, it has to be 0 somewhere. We've now found somewhere that the function is 0.
It does need to be, remember that in order to use IVT, it needs to be continuous, but it's a polynomial. So
and polynomials are super continuous. Yes. If you were writing this on an exam and you were citing the EVT, make sure that you say because the function is continuous. When writing solutions, that information is very important. So then the question is, how do we know that there's not a second root in this interval? Which I love the argument here. So one of the arguments, so this is the core of the argument. I'm just going to put this on the slide. Then I'm going to explain verbally why it's true. If there were a second root in this interval, we would have 2 local extrema in the interval. But the derivative is only 0 once in the interval because the derivative has 2 roots. It's a quadratic, and one of the roots is at 0. The other one is somewhere in this interval, but where it is doesn't actually matter. What matters is that it's only 0 once in this interval. So it can only have 1 extrema. But if we had 2 roots, we would have at least 2 extrema. And here's why. If we had, so let's think about cases. If all 3 of them are single roots, if the function has 3 single roots and 2 of them are in this interval, the third one would also have to be. Because the first one would take us negative to positive, the second one would take us positive to negative, and the third, we would need to get positive again before 2. So the third one would also have to be in this interval.
I'm gonna draw while you're doing this, because I think it's helpful.
Also feel free to draw this in your notes if you are unconvinced by what I am saying. Drawing this kind of picture is incredibly helpful. What we could then do is get 2 extrema by first looking between the first root and the second root, and then looking between the second root and the third root, and we would get 2 distinct extrema. And this would contradict the derivative only being 0 once in this interval.
And this is the situation that Nick has described. In order to have at least 2 single order roots that pass through it, you have to also have a third one in order to come back down. So you go down, up, and then there's not another one. How are you going to get down here? Because we know that our function ends up here when x is 2. These points are what we know about our function.
The second case is that we have a singular double root. But again, we get a local extremum there, where the double root is, it happens with multiplicity too. In a double root, though, you kind of bounce off the x-axis, and so you get a local minimum there. But our function would also have an extremum between where it started and the first. Whoa, wait a second. Yeah.
Where it started in the first. I drew the local thing. I drew the second order after the first order. Are you thinking even the other way around?
It doesn't matter, but yes. You would get one extremum between the first order root and the second order root, and a second extremum at the second order root. The reason there's an extremum between the first order root and the second order root, you can even just apply the mean value theorem. You can say, okay, between these points, the average rate of change is 0. So there must be a point between them where the derivative is 0. Either way, and actually there it doesn't even matter that it is an extremum. But no matter what, in every single case, we ended up with the derivative having 2 zeros in this interval if the function had 2 zeros in this interval. But we know that the function only has 1 zero in the interval.
You mean the derivative?
Sorry. We know the derivative only has 1 zero in the interval, and so this forces the function to only have one derivative, or this forces the function to only have one root in the interval. Now, that proof was mostly delivered verbally. How you would write that down is something, again, I'll be happy to go through once I have some pizza in me and you have some pizza in you and it's the Q&A. But the way that you came up with that, the way that I came up with that was a picture. I drew what it would look like if there were 3 roots, because I noticed here that when you take the derivative, you get 3x squared minus 6x. So I noticed that the derivative had to have only one root between 0 and 2. And so you could only have one extremum. And then I just drew through the cases for having multiple roots in that interval and found that there had to be multiple extrema. So we're going to go through Taylor series real quick. We have 3 slides on it. And after the 3 slides, we get pizza. Power through. You guys can do this. That was actually mostly for me. I'm so hungry.
Yeah, you take Taylor series.
Okay, awesome. I will be taking Taylor series because I don't like them, but they're fun. So I have an exercise for everyone. By hand, without a calculator, can you compute the sine of 0.2? Thanks. This is, wow, you guys are doing it in your heads. You're so good. But no, this is like infeasible. Like, this is not something a person can do. Compare this with the following thing. Compute 0.2 minus 0.2 cubed over 6. Now that is also, at least for me, not the easiest to do in my head because I'm atrocious at division, but that one at least feels possible. The latter approximates the former to at least 5 decimal places, and it's so much easier to handle. In general, it is the case that polynomials are much, much nicer than things that are not polynomials. Right? Like, polynomials are incredibly easy to take the derivative of. It's purely symbolic. The sum of polynomials is polynomials. And it's really easy to evaluate polynomials at points. Polynomials are also much nicer in proofs. So a general question of interest is, how can we approximate an arbitrary function with a polynomial? Now, there's a famous theorem called the Stone-Weierstrass theorem, which you guys do not learn, but I think is worth mentioning, that tells us you can approximate any continuous function with a polynomial. However, the Stone-Weierstrass theorem does not give you the polynomial explicitly. If the function is differentiable, though, we can explicitly write down a polynomial that approximates it well. How do we do this? Okay. So let's just say we want to approximate a function f of x near x equals 0 by a polynomial p of x. If our approximation is any good at all, the value of the function should clearly equal the value of the polynomial.
Actually,
right?
What I did last time. I'm going to also draw while you're drawing.
The value of the function should equal the value of the polynomial. So we want f evaluated at 0 to be equal to our polynomial at 0. If we write our polynomial in this form as like a sum of coefficients and powers, then the polynomial at 0 is just going to be the constant term. Oh, god damn it. I wrote a 0 equals 1 because I was still stuck on this. I was originally going to do this with a concrete example of cos x, that I went the concreteness doesn't help. A0 should equal f of 0. That is a typo. A0 equals f of 0.
I do sin x here. Yeah.
So the thing is, if we just took our polynomial to be like constant, it would be a very good approximation right at 0 and a very bad approximation everywhere else. So kind of the thing that we want is not just for our function or our polynomial to equal our function. We also want our polynomial to change like our function. How do we control the change of the function? We work with the derivative. So we also want the derivative of the polynomial at 0 to equal the value of the derivative of the function at 0, because by establishing this condition, we will make our polynomial change similarly to our function. If we look at what the derivative of the polynomial is, okay, the constant term disappears when we take the derivative, then it becomes a1x plus 2 times a2x, plus a1 plus 2a2 plus 3a3x squared and so on, whatever. If we evaluate the derivative at 0, all of the higher terms cancel and we're just left with a1. So to make the derivative of the polynomial at 0 to be equal to the derivative of the function at 0, we set a1 equal to f prime at 0. So now we have the constant coefficient and the linear coefficient. And these two things will ensure that our function has the correct value and that it has the correct derivative. So our function will evaluate correctly and it will change correctly. But just a linear function doesn't curve, and functions curve, right? We want the concavity to be correct. We want the curvature to be correct. And so to make the concavity, the curvature correct, what do? We make the second derivatives equal. We make how the derivatives change the same. And so we set the second derivative of the polynomial equal to the second derivative of the function, and the third and the fourth and so on. And let's explicitly solve for this. The kth derivative of the polynomial is k factorial, evaluated at 0, is k factorial times the kth coefficient. So in order to make the kth derivative of the polynomial equal to the kth derivative of the function, we set the kth coefficient to be equal to the kth derivative of the function evaluated at 0 divided by k factorial. And at this point, this should look very familiar, because these are the coefficients of a Taylor series or a Taylor polynomial. What this is basically saying is that if our function is differentiable, we can pick the coefficients of our polynomial so that as many derivatives as we want agree, and this will give us a good equality. Now, there's a problem here that I'm not even going to bother going through in detail right now, but basically the Taylor series of a polynomial is equal to the polynomial itself. And the only notable thing here is that if the polynomial, if you write the polynomial in standard, I guess it's worth mentioning quickly, to do this around a point other than 0, you replace every single 0 or every single x with x minus a. And this just translates everything over to 0, and then you do the exact same thing again. To do this problem, essentially all that you do is you write your polynomial in this form, and then you compare the derivatives. And so what this theorem tells you is that the Taylor polynomial is the only polynomial that has all of the same derivatives as your function. So this gives you a nice uniqueness, and it's also a good clue that how we built this Taylor polynomial gives us a good approximation of the function, because this is the only polynomial that will have the correct value and all of the correct derivatives. How good is it? Oh, god damn it. Kind of using Taylor series, there's like an elementary application of Newton's method. Newton's method is just for finding out where a function is 0. Basically, what you do is you guess a point. Near that point, you approximate the function with a line. You check where the line is 0, and you guess that as your new point. And the reason we would expect this to work is that near a point that is like the function's well approximated by the line. So the function's 0 should be close to where the line is 0. And so if we keep guessing like this, we should get sequentially closer and closer and closer to where the function itself is actually 0. And over here, I show an explicit derivation of the formula. The reason I show this is not because you actually super need to memorize it here, but the point is more that I do not have Newton's method memorized. However, I understand how it works. I understand the principle of approximate our function with a line, which is just like the degree 1 Taylor series, check where it's 0 and guess again. Did I mess up the formula? I may have messed up a division. But either way, you can rederive this formula if you understand the principle it comes from. Math 137 does not have to be memory bash. If you conceptually understand these derivations, you can do them yourself. So the last thing worth mentioning is that since Taylor series are approximations, we care about how good those approximations are, right? Like if you're approximating a quantity, you want to know how far off you are. And Taylor's theorem tells us that the error, the difference between the polynomial and the Taylor series, is going to be bounded by the first derivative, or sorry, the next derivative at some point times this factor. And all I want to point out here is that this looks a hell of a lot like the mean value theorem, right? We have the remainder being bounded by or the error being bounded by the derivative at some point. The reason this basically shows up is that at x equals a, at the center, our error is 0. And so we can evaluate the average, or sorry, the maximum of the error by looking at the average rate of change of the error. And so the way this, like the way the proof of Taylor's theorem proceeds most of the time, is to say, okay, we're bounding how fast the error changes, then they bound that in terms of a derivative and go from there. I also just want to point out that this theorem completely trivializes the polynomial problem, because if you have a polynomial of degree n, the n plus first derivative at every point is 0, so this tells you the error everywhere is 0. And I just thought that that was a cute little application. With that, we finish all of the content that I have prepared, and so it's time for pizza. Cecilia. How are you doing? Want me to yell that? One's like reversing? Okay, give me a second. Give me 1 second. 1 slice per person to start. If there are leftovers, we'll give you more. We put up on the board.
Yeah, I got it right here. I got it right here. So it's basically to show that